good afternoon. We are with chapter number 36. I just introduced this chapter last class. Okay, so I told you that inductors are simply circuit elements which can be used to store magnetic field. Okay, they are analogous to capacitors in electric field. So the simplest of an inductor is going to be a solenoid. You can see here a solenoid. Let's say there is a current I in the solenoid. So from the right hand rule, you know that the magnetic field I is as given in the picture here. So the current is producing a magnetic field. So if it's producing a magnetic field, then you know that there is a magnetic flux also. Okay, that magnetic flux is going to be phi b is equal to integral b dot dA, which is going to be b into A because the magnetic field is uniform. Okay, and you know the expression for B is equal to mu naught Ni, where small n is the number of turns per unit length. Okay, so this is a uniform magnetic field, direction given here. Now, if this current is changing as a function of time, if this current is changing as a function of time, if B is a function of time, that would imply, if the current is a function of time, if the current that you're passing through the wire is a function of time, that would imply that magnetic field is a function of time. That would imply that the flux is a function of time. That would imply that there will be an EMF and a current and an induced current. Okay, so these two are coming from Faraday's law. Okay, now since this EMF is produced in an inductor because of the action of the inductor itself, we will call this EMF as EMF with subscript L. This L stands for inductor. And you can see that, okay, you normally from Faraday's law would tell you that the EMF is proportional to d phi b by dt. But since phi is going to be proportional to the current, you can also say that EMF in the inductor is proportional to di by dt. I hope this point is clear to you. EMF induced is proportional to the rate of change of flux. Flux is in turn proportional to the current. Therefore, you conclude that the EMF is directly proportional to the rate of change of current. Okay, so that's how this equation is coming. Or now what you can do is, this is a proportionality. You can make it an equation if you have a proportionality constant. That proportionality constant is going to be L, the inductance value of the given inductor. Therefore, the EMF induced in the inductor is equal to L into di by dt. Okay, and this L is called the inductance. Straight away from here, you can get what is going to be the unit. The unit is going to be EMF is voltage, time is second, divided by current is ampere. So voltage second per ampere is 1 unit, which can be called as Henry. Okay, and please remember, L is always a positive quantity. There is no negative value of inductance, just as there is no negative value of capacitance. Now I'll give you the analogy for that is going to be in capacitors. We have seen that in capacitors, we have seen that the charge on the plates is directly proportional to the potential difference. Therefore, you wrote that Q is equal to C into delta V. And C is always a constant. So this is for a capacitor. Okay, whereas for inductor, this is the way you get the definition for inductance. Their charge, here it will be current. Okay, so you have to just see this one-on-one correspondence. Now let us introduce, when we are saying EMF, then this EMF is going to give rise to an induced current in which direction? So that's the next question. For that, we have to go to Lenz's law. And before that, I also want to tell you what is inductance. Inductance per se is the ability, the inductance value. If I say 9 millihenry or 3 millihenry, these actually denote the ability of the inductor to store energy in the magnetic field. So now let us come to Lenz's law applied to the situation. So here is your, first you forget this guy. First you forget this EMF is initially not there. There is a current I passing through the inductor, and now let us decrease this current. Let us now decrease this current. If this current is going to decrease, that means the flux is also decreasing. If the flux is decreasing, okay, flux is decreasing means d phi by dt is negative. Okay, d phi by dt is negative. Therefore, you are going to get an EMF in the direction of the magnetic field or current. You're going to get an EMF to oppose this decrease. Therefore, it is going to be in the direction of the current or the flux. Okay. Now, what happens if current is decreasing? If current is decreasing, di by dt is negative or d phi by dt is going to be negative. Therefore, there will be an induced current and the corresponding flux or magnetic field in the opposite direction to counter that increase. Okay, now you look at this. Already there is a current in the circuit. Then you are getting an induced EMF, and you've seen in the previous chapters that induced EMF will give rise to its own current. So what happens is the net current in the circuit is going to be decided by which is greater. Okay, the net current is going to be the original current plus the induced current. If these two currents are in opposite direction, you have to subtract one from the other. Okay, but if both are going to be in the same direction, we just have to add them. And anyway, that part is not important. So let's just go to Lenz's law. So Lenz's law tells you that the induced EMF is opposing the change in the flux. So what is this induced EMF? Please listen to me very carefully. What is induced EMF? This induced EMF is going to be the potential difference between the ends A and B. The potential difference between ends A and B arising because of the induced EMF. Don't bother about the original current. According to the original current, your B is going to be at a lower potential than compared to A. That is why the current is flowing. So don't just forget that. Now let us look at the potential difference created between A and B because of the induced EMF. So if the induced EMF is in this direction, okay, so the induced EMF is VB minus VA. It is VB minus VA. That's the definition of the induced EMF. And that's going to be equal to minus L di by dt. We are putting a minus here. This minus is coming from Lenz's law. It comes from Lenz's law. So now look at this. If a current is flowing in this direction, if the EMF is going to be in this direction, induced current is in this direction. So VA should be greater than VB. As far as the induced EMF and the induced currents are concerned. Now, the next exercise that we are going to do is we are going to find out the inductance expression for different types of inductors. There in capacitors, we had parallel plate capacitor, then we had spherical capacitor, we had cylindrical capacitor. So here also we have two geometries of inductors. One is going to be your solenoid, another is going to be your toroid. Okay, so for these two, you have to get the expression for the inductance. So how do you do that? There is a method. So first thing is find the flux through the device. To get the flux, obviously, you need to get B. Then you have to integrate over cross section. So you have to get the flux. Next, what you do is use Faraday's law and get the expression for the induced EMF. After that, put that in this expression, EMF is equal to minus L di by dt and get your L. Okay, now when I'm talking, it sounds like Greek and Latin. So let us actually do it. Before we go there, I just want to introduce an expression called flux linkages. So for that, what we'll do is, let's say we are talking about a solenoid. And let there be n number of turns of the solenoid. See, look at this. If I take one turn, and if I talk about what is the flux through that one turn, let phi b be the flux through one turn. Okay. Now, the flux because of the n turns, you just have to add up each of them, or in other words, you have to multiply by n. You get the net flux through the solenoid. or through the inductor, where n is the number of turns. Now this n phi b has got a name. It is called flux linkages. It is called, don't think that madam has made some English mistake. No, it is flux linkages. That's the name of the term. It's flux linkages. N into phi b is called the flux linkages. Okay. So now let us go and see what is the induced EMF. The induced EMF in this inductor is minus L di by dt. Okay. This minus comes from Lenz's law. Now, from Faraday's law, this comes from Lenz's, I'm sorry, this L di by dt came from this chapter with a minus sign that came from Lenz's law, whereas this comes from Faraday's law plus Lenz's law. So what is it? EMF is equal to minus d phi b by dt if it is one turn, and n into d phi b by dt if it is n number of turns. So what we'll do is we'll take n into the expression and then write it as n phi b. Okay, or you are now getting a new definition for the induced EMF. You're getting a new definition for the induced EMF. So this implies that the induced EMF is negative of rate of change of flux linkages. Time rate of change of flux linkages. So induced EMF is minus d by dt of n phi b. Please, this comes from Faraday's law and Lenz's law. Now, from making a comparison between these two terms, you are able to write that. Okay, what you can now do is you have to make an integration with respect to time. So L di will be equal to n phi b. L di comes from here. L di will be equal to n phi b. Now do an integration. When you do an integration, okay, and what is the integration you're going to do? You're going to make an assumption that at a time t equal to 0, the current in the circuit was 0, and at a time t equal to t, the current is I. Current is 0 means phi b is 0 initially, and then phi b finally. So therefore, what you will get is L into I is equal to n phi b. L into I equal to n phi b, or I'm going to get I is equal to n phi b by L. Okay, sorry, L equal to, let me not bother about current. I'm interested in L. I want to get an expression for L. So L equal to flux linkages divided by the current. Okay. So this is the general expression for inductance, inductor. So the inductance expression is n phi b by I. Now I'm going to tell you something important. Is phi b related to current? After listening to all these stories, just answer this question. Is phi b related to current? Is flux related to current?
Yes, ma'am.
Yes. It is related to current because current was responsible for magnetic field. Current was proportional to, the magnetic field was proportional to current, and flux is proportional to the magnetic field and thereby the current. So what you can do here is you are able to see that L is equal to N into integral P dot dA divided by I, which is N into mu naught small n I dA divided by I and I goes. I and I will go. Or you are able to come to a very, very important conclusion. The conclusion is that since the magnetic flux is proportional to current, we have shown here, magnetic flux is proportional to current. Current and current in the numerator and denominator will cancel out. Therefore, you are able to see that the inductance of an inductor is independent of the current. It is independent of the current. Does this remind you of something? Does this remind you of something? Inductance value does not depend on the current. Does that depend you of something? Something from electrostatics or capacitors? Anyone?
Capacitance does not depend on the charge.
It does not depend on the charge. Who is this person who has answered this question?
Kiranmai, ma'am.
Kiranmai, you will do very well because your logical thinking is there. I'm very happy. Okay, there's at least one person who is able to think like this, shift the thinking like this, parallelly. And if you do this, your learning will be easier. It will be fun also to learn. So you're seeing that the inductance does not depend on the, oh, I've written the answer here. No, but still, Kiranmai, I know you're a good student. Okay, so the inductance is independent of the current. It only depends on the geometry. How do I say that it depends on the geometry? Anyone? How do I come to the conclusion that it depends on the geometry? Anyone? Capacitor also, we said the same thing. Capacitance of a capacitor does not depend on the charge, it depends on the geometry. Like that here also I'm saying, it depends on the geometry. This N phi b by I, does it have geometry? What is N? What is N? Number of turns, that is geometry. Then what is phi b? Phi b is B into A. What is A? Area of cross section. That is also geometry. Are you understanding? So the inductance value depends on the geometry. How many turns are there? What is the area of cross section? That is simply geometry. Okay, now we got a general formula. Now we are going to do this for two specific inductors. One is going to be solenoid. Solenoid is similar to your parallel plate capacitor. Okay, so now let's see that. Okay, you have a solenoid, and inside a solenoid, the magnetic field is given by B is equal to mu naught small ni, where small n is the number of turns per unit length. So now what will be flux linkages? Flux linkages will be N phi B, which is N into L. N into L is equal to capital N. Small n into L is equal to capital N. Then of course, it has got a uniform current, a uniform magnetic field. Since the magnetic field is uniform, for a solenoid, this is B dot A is BA. Okay, so you will get N into L into B into A. Now, what is B now? B is equal to mu naught into small n I. B is equal to mu naught into small n into I. Okay, now let's simplify this. You will write it as N square I mu naught L A. Okay, so this is your flux linkages, N phi B. Now we already saw that L equal to N phi B by I. This was a general expression that we had got recently. So there you put this flux linkages. You will see that I and I will get cancelled out. You will get L is equal to N square L mu naught A. So once more, you are seeing that there is geometry involved. N, L, A. Okay, so it depends on the geometry of the inductor. And of course, you can also see inductors. Normally what happens is, you will not be talking about the inductance per se. You will be talking about inductance per unit length. Now let me see whether Kiranmai is able to answer. Did we see something similar in chapter number 20, in chapter number 30? Here we are saying inductance per unit length. Like that, did we see something there?
Capacitance per unit length.
Length of which capacitor? Do you remember that? Cylindrical capacitor. Cylindrical capacitor. And there I gave you the example of the cable which comes to your TV set. Okay, those are capacitors. They are cylindrical capacitors. Similarly, when you're talking of inductors also, you can talk about inductance per unit length. Okay, so this expression you got. Next, I told you two types of capacitors we are going to see. One is over. The next is toroid. Toroid, I hope you remember from chapter number 33. In chapter number 33, we have seen that if you take a solenoid and if the solenoid is bent so that the ends meet, then what you get is going to be a toroid. And remember, toroid need not have a circular cross section. I remember somebody in the class giving me an example of a donut. Okay, so a donut normally has a circular cross section, but then a toroid need not have a circular cross section. It can even have a rectangular cross section. Like for example, you see here, this picture is giving you a part of a half of a toroid it's showing, but the cross section is a rectangle. So it can have even a rectangular cross section. Okay, now we are again going to go back to chapter number 33 for some of the results. Okay, one of the results that you're going to see is going to be that there is going to be a magnetic field in this region inside the toroid. Okay, if the inner radius is A and the outer radius is B, then for R less than A, the magnetic field will be 0. We got it from Ampere's law. For R greater than B, also magnetic field will be 0. That also we got it from Ampere's law. But for A less than R less than B, for this region, that is for points inside this rectangle, there will be magnetic field. And the magnetic field is going to be given by the expression mu naught capital N I by 2 pi R. Mu naught I by 2 pi R for one wire. So n wires are there, n turns are there. So mu naught capital N I by 2 pi R. And what is this R? R is the distance from the center of the toroid to any point that you are interested in. Okay, so mu naught N I by 2 pi R. Or you are seeing that the magnetic field is a function of R. Since the magnetic field is a function of R, therefore, flux has to be obtained only by doing an integration. If B was uniform like in a solenoid, then we could have simply said B into A. But here you need to do an integration. So if you have to do an integration, this step is crucial. Please listen. So what we are going to now do is we are going to get the expression for the flux. So integral B dot dA. So let's substitute. So okay. So what we'll do is we are going to do an integration. And what is the variable? Let us see. What's going to be the variable? Let us see. So integral B is mu naught capital N I by 2 pi R. And what is this dA? What is this dA? dA is going to be, listen very carefully, dA is simply going to be a rectangle. dA is going to be a rectangle. This is dA. And look at my figure. The height of this rectangle, that total rectangle is h, and the length is going to be b minus a. The length is going to be b minus a, and the height is h. Height is h. So within the big rectangle, I am going to take a small rectangle of area dA. Okay, and my dA is going to be equal to h into dr. My dA is going to be h into dr. Okay, h is the height and dr is the width. Therefore, h into dr. And you should choose your dr so small that the magnetic field is the same at all points on this tiny rectangle. On this tiny rectangular area, the magnetic field should be the same. So you should take dr as small as possible. So instead of dA, what we'll do is we'll put h into dr. And another thing we are doing is that we are taking our A vector and B vector parallel to each other. Therefore, no minus sign will be there. Okay, now what we'll do is we'll take out all the constants. And R, in which region are we going to do this integration? We are going to do it in the region where there is magnetic field. You know magnetic field is there between R equal to A to R equal to B. Okay, so now what you do is take out all the constants. So what are all the constants that are there? Let's see, mu naught, capital N, H, I by 2 pi, all these are constants. Take them all out of the integral, and then what you get is integral dr by r. You know that integral dr by r is log r, limits a to b. So what will this be? Log b minus log a, which is log of b by a. Okay, so just do that. You get log b by a. So you finally get this as your phi b. Then of course you know L equal to N phi B by I. So you know that N, you have to multiply by N, capital N, so you get an N square here. And then I and I will go because you divided by I. So once more, you're seeing that the inductance for a toroid is not depending on the current, it depends on the geometric factors. Geometric factors are A, B, capital N, H. So it depends on the geometric factors. Okay, now let us go to, till now we discussed inductors which are hollow inside, air-filled uh, inductors. Now what we'll do is, we'll fill it with a core. We'll fill it with a core. This is analogous to what we have seen in capacitors. First you studied an empty capacitor, after that fill the space inside with a dielectric slab. And in the previous chapter you studied the use of a dielectric. Similarly here, inside your inductor, you're going to fill the space with a core. That core material is going to be ferromagnetic material. You're going to fill it with a ferromagnetic material. Or let's say you're going to fill it with a material with a kappa M. Okay? And what happens, you have seen in the previous chapter, in chapter number 35, you have seen that whenever you fill a space with a ferromagnetic material, then the applied field B naught becomes kappa M into B naught. It increases by a factor kappa M. So that's what will happen here also. Here also the magnetic field will increase. Okay, and already you've seen that L is proportional to, okay, since B is proportional, L is going to be proportional to B. You're going to see that L is proportional to B. Therefore, you're going to see that when you fill the inductor with a ferromagnetic core, then your L value also increases. If the empty inductor had a value L naught, then after you fill it with a ferromagnetic material, it becomes kappa M into L naught. And please don't use paramagnetic or dielectric materials, because I told you for them, kappa M is very, very small. It's just around 1 only. But then if you go to ferromagnetic materials, it can go from hundreds to thousands also. So by 1,000 times, 2,000 times, you can increase your magnetic field. So this is the reason why any electromagnet will have iron core. So you come to the conclusion that the inductance of an inductor can be increased by filling the inductor with ferromagnetic material. Okay, now I've been telling that capacitors can store energy in electric field. So similarly here you're going to see that inductors can store energy in the magnetic field. For that, what the author does is, there I don't know whether you remember, I was talking of two plates and then you increase the distance between the plates. What happens? There is an increase in field, there is an increase in the energy storage. That happened because an external agent did work and put energy into the system and pull the plates apart. We have seen there. And then we come to the conclusion that because it is actually the distance between the plates that changed that energy, we came to the conclusion that energy is stored in the electric field between the plates. Similarly, here what happens is, you take two parallel current carry wire. You know that they attract. Okay? And you also know that between them, there is magnetic field everywhere in the vicinity. Now, to pull them apart, to increase the gap between them, an external agent has to do work. Where is that work going? That work is going and getting stored in the space between the two wires. It cannot get deposited on the plates, on the wires. So where is it going? It's going into the space between these two wires. And what is there in the space between the two wires? What you have is magnetic field. So you conclude that you are storing energy in the magnetic field. Now what happens when you allow these two wires to come together? When you allow the two wires to come together, they are doing work. The system is doing work. System is doing work means it is expending energy. It's using energy. So that energy is recovered. Okay. And straight away we go to the expression for the energy. Straight away we go to the expression for the energy. The expression for the energy stored in a capacitor is UB is equal to half Li square, analogous to half Q square by C. what did I put that? Put here, one sec. Analogous to half q square by c. Half q squared by c for a capacitor. Of course, you can also talk about energy density. Same thing can be done here also. You can talk about energy density. So what will be the energy density? Anyone? Energy density will be total energy divided by the volume if the energy distribution is uniform. If the magnetic field is uniform, similar to parallel plate capacitor. So here you see energy density, like in that chapter, here also we are using italics, a small italic U for energy density. It is total energy divided by the area, by the volume. So the volume in the case of a solenoid is the length into area of cross section. Okay, so let's just do it and see. Half Li square divided by Al. And for a solenoid, it is, you know, the expression for L. Okay, substitute it. I square divided by Al. A and A cancel out. Okay, so what are you finally getting? Let's say you get, there is only one mu naught in the numerator. So you will get half n square L. L and L also cancel out. Half n square mu naught I square. Okay. Okay, so this is what you're getting. And when you see this, how you wish that there was one more mu naught there? Because you know that mu naught small n I is magnetic field. So what we'll do is you will multiply and divide by mu naught. Okay, so when you do that, what you're getting is half into mu naught ni whole square by mu naught. And you know what is mu naught ni? Mu naught ni is magnetic field. So magnetic field square by mu naught. So this is the expression for the energy density. Okay, and this is analogous to half epsilon naught E square. So you see here, the energy density in the solenoid is proportional to D square. Similarly here, energy density in a capacitor is proportional to square of the electric field. And please, we have derived this expression for a solenoid, but the same expression can also be used for a toroid. Only thing is, in the case of a toroid, B is not the same at all R from A to B. Okay, so that means the energy density will be different for different values of R. However, if you know the magnetic field at a point, you can straight away use this expression and get the energy density. Okay, we have finished this chapter. Let's quickly see whether you are able to do these problems. The inductance of a closed pack coil of 400 turns is 8 millihenry. Calculate the flux through the coil when the current is 5 milliamp. Inductance of a closed pack coil. So that means assume it is a solenoid. So what is 400? Number of turns. And what is L? L is 8 millihenry. Then the current is 5 milliamps. You have to get 5B. Can you do this? Did we see some relationship between L and 5B minutes back? This is what we have seen. Okay, so you can see that flux through a turn is, of course, you have to put an N here. So calculate the magnetic flux through the coil. So that means you have to find N phi B. N phi B equal to L into phi. Okay. Then try this one. At a given instant, the current and the induced EMF are as indicated in this figure. Okay. Is the current increasing or decreasing? Anyone? The current is in this direction, magnetic field is also in this direction. If the current is increasing, the increase in flux is also in this direction. Then in which direction will the EMF be? According to Lenz's law, it will be in the opposite direction. Since the EMF induced is in the same direction as the current in the wire, you conclude that the current is decreasing. Next, EMF is 17 volts. Di by dt is 25 kiloampere per second. What is L? What is L? EMF is 17 volts. Di by dt is 25 kiloampere per second. What is L? What is there? EMF is equal to L di by dt. That's all. Okay, now this one. A toroid has, let's draw the cross section. Okay, a toroid has 5.2 centimeter square cross section. It is not a rectangle, it is a square. Okay, the inner radius is 15.3 centimeter. Obviously, you can find out what is the outer radius. B will be equal to A plus 5.2 centimeter. So that's not difficult. Next, it has got 536 turns and carries a current of 810 milliampere. Calculate the inductance. Calculate the inductance. Anyone? You don't have to give the answer. Which way to do the problem? Can someone say? What? Inductance is going to depend on various factors like N, A, B, etc. So look at the formula, get your inductance. Then find the magnetic flux. So to do the magnetic flux, what should you do? Mu naught capital N I by 2 pi R, that is your B. Then dA, to do dA, take a small dr. So what you do, 5.2 meter into dr. Do the integration from A to B. You get the flux. Okay, so just go through these things. The video is there, look at that. Okay, I'm not going to do all this and show you. I'm just trying to show you how numericals can be there. This is what I've done. This last one is the toughest possible. Okay, so you can't be asked the entire problem. You may be asked parts of this. Anyway, you should know how to find the flux. Anything you want to ask regarding this chapter? Okay, if nobody has anything to ask, I'll stop presenting. Okay, so this is a very short chapter, but what I want to, small word of advice to you all, please don't neglect these last few chapters. These small chapters, they will also get a lot of questions. There will be questions from those chapters also. So don't miss out these last few chapters. The next chapter also requires only 2 classes. Okay, so Monday, if I take a class, if I take a special class on Tuesday, I can finish the syllabus. Otherwise, on Wednesday, I can take a class and finish it. Okay, that choice is yours. You people can decide on Monday and let me know whether you want a Tuesday special class or you want me to come on Wednesday and take the last class. Anyway, with this batch, I'm going to have a problem. If I see you on the campus also, I won't recognize you. You will recognize me, but I won't recognize you. Okay, so good day everybody. You can leave.